Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Alright, Alhamdulillah. I hope everyone is having a good time for the past week during midterm break. Alright, so we have learned about Laplace transform. What is Laplace transform? And how we convert from time domain to frequency domain, which is S domain. Okay, so today we are going to learn about the properties of the Laplace transform. Okay, so there are 6 properties. The first one is time shift, frequency shift, time differentiation, time integration, time convolution and frequency convolution, and also initial final value. Okay, so actually these two are related, and these two also related, and this one convolution and frequency convolution, and the last one is the initial and final value. Alright, so actually these properties have been calculated and tabled out in the Laplace transform property table. Okay, if you can see, we have addition, multiplication of a constant or scalar, time differentiation. So using time differentiation, we have many degrees of differentiation: second degree, third degree, and until n degree. Right? So for addition, we will add two type of signal, and we will convert it one part by part. Okay, and then we have time integration, time shifting, frequency differentiation, in frequency integration, scaling, time convolution, frequency convolution, initial value, and final value. So it just like what the outlines, but we will go into detail. Okay, so for the first one, the linearity or addition or additional property. So what does it mean? It means that if we have two function in time, okay, with a1 and a2 as the coefficient, if you want to convert it into S domain, okay, we can just convert it part by part, which is f1s from f1t, and then f2s from f2t, and then we can add it, and the value will be equivalent, which is it is a linear, okay, or superposition, or we can call it also additional properties. Alright, the second one is scaling. If we have a frequency, we have a functions f a t multiplied by the value of a. In the time domain, we just change it to fs, but we have to divide the s by a and multiply it with 1 over a. And then for the time shift, if we shift a frequency by a value at the time minus a, this is step functions to make sure it start at minus a, and also it delayed or shifted by minus a. So in frequency domain, we will multiply it by e minus s and also the value of a. Okay, and then this is the function ft. Okay, this one you don't have to shift, but you will shift it in the value of exponential. Alright, so this is a linearity property or a superposition. That means you convert xt to xs and yt to ys, and then you just add. Alright, time shift. Okay, if you shift the function by value of t naught, okay, you will transform the function xs, and the shifted value you will put it in the form of exponential. Okay, so usually we will identify the function by multiply by ut, to make sure it is causal or t larger than 0. Okay, and then you just shift the frequency to Laplace and multiply it with e minus s, and this is the value of the time shifted. Okay, for example, we have these functions. This function is actually a combination of t minus 1. It is a function t, and then also it is a step function from 2 to 4. Okay, so there are two conditions, 1 and 2. Okay, so we will define it by t minus 1, but it exists from t minus 1 until t minus 2, which is also equivalent to here. So this is ut minus 1, and then this is ut minus 2. Okay, it only exists here, so it will make the first portion of the equation. So this is 1. And then the second one, which is this one, exists from ut minus 2 minus ut minus 4. This is ut minus 4. ut minus 2. Okay, so it will exist here. Okay, so the combination of these two will make this function. Okay, so we will multiply it step by step. So ut minus 1 multiplied by ut minus 1, so it will become here, and then t minus 1 multiplied by ut minus 2, so t minus 1 multiplied by ut minus 2. Okay, so the second one, it's just the same because we don't multiply it with t minus 1, so ut minus 2 minus ut minus 4. Okay, so in this section, okay, you will see that the delayed is t minus 1, but the ut is t minus 2. Okay, so we will make it similar to the step to the first, to make it similar with t minus 1, and also the time also t minus 1. So we expand this function t minus 2 plus 1, which is also same with t minus 1, okay, which is this one. Okay, and then multiply by ut minus 2. So that means we are going to expand it by t minus 2. We take this one, multiply by ut minus 2. So this part will be same, the shifted minus 2 at ut and also t minus 2. That means they will be shifted at the same time 2. And then the second one, this one, 1 multiplied by ut minus 2. Okay, so we put here. Okay, now this equation, which is from this equation, okay, we put it here back. So insert back here. So t minus 1, ut minus 1, minus, this is the one that we add just now. Not add, expand. Okay, t minus 2, ut minus 2 here, plus ut minus 2. Okay, but this one is minus, so this is plus. So this one actually can be cancelled out. Minus ut minus 4. Okay, so now we have 3 terms, 1, 2, and 3. Okay, so t minus 1 ut minus 1 means that it is shifted by 1. So we know that t in Laplace is 1 over s squared. Okay, and then the shifted by minus 1 is represented by e minus s. Okay, the next one is also a t. So when we convert it to Laplace, it will become 1 over s squared. But the shifted value of minus 2, we represent it in the form of exponential e minus 2s. Right? And then the third one is ut minus 4. We know in the table, if ut we convert into Laplace is 1 over s, and the shifted is minus 4. Okay, so this is the answer for the Laplace transform of this graph. Okay. Alright, the second example, if we have a signal of s plus 3 plus 5e minus 2s divided by s plus 1 multiplied by s plus 2. Okay, we will separate this into two form, which is s plus 3. Okay, the first one. And then the second one is 5e minus 2s. Okay, if you see in this form, we will see that this one, okay, can do partial fraction equation, PFE, and this one is a common transformation with the numerator of 5, but it is shifted by 2 seconds, okay, minus 2. Okay, now we call this one x1 and this one x2. Okay, this one x2. Okay, for x1, s plus 3 divided by s plus 1 multiplied by s plus 2. We will separate this part by part. So find the value of a and b. So the value of a is 2. Okay. And the value of b is 1. Okay. Using PFE, partial fraction equations. That means you separate these two of the two denominator. Okay, and then the second one is 5s plus 1 s plus 2, but remember that this one have shifted value of 2. Okay, so now we just convert this function x1, this is x1, this is x2, okay, into time domain. Okay, so for 2 divided by s plus 1, that's mean 2 with e minus t, we convert into time domain. And the second one is 1, is the coefficient 1 here, 1 e minus 2t. It is exponential with alpha or a equal to minus 2. Again, this one, 1 is here. Alright, that is part 1, x1, okay? And then for part 2 is equivalent to 5. 5 is the coefficient, we put it outside. And then this one is exponential, e minus t. And this one is exponential with the value of alpha is 2. Okay. Alright, now we want to combine this function to e minus t minus e minus 2t ut. Okay, and then the second one is 5 e minus t minus 2. Where did we got this one? From the shifted value of 2s. Okay, so this is additional information from the x2. Okay, so it will start at ut minus 2 because it shifted here by 2. Right, so this is the answer for this question. Okay, first of all, you have to know how to do the partial fraction equations and then identify the shifted value at the second equation or x2. Right? The next one is the time scaling or frequency scaling property. Actually, these two will be inversely usable. Alright, so if we see that in time domain, it is multiplied by a, and the frequency domain, we will divide it by 1 over a, and s also divided by 1 over a. Okay, if it's frequency scaling, this means in the frequency domain, it's multiplied by a. Okay, in the time domain, it will be divided by a, and t also divided by a. Alright, for example, we know that for sine, the Laplace transform is omega divided by s squared plus omega squared. Okay, but now we want to multiply this time domain with amount of 2. Alright, so this is a, for example, just now, just like this one, a. Okay, so now the value of a is 2, so we have to divide here, divide by 1 over a, divide by 1 over a. Okay, and then the s also divided by 1 over a. So s divided a is 2 squared plus omega squared. Okay, so if we simplify this one, we will get this answer. So it's already scaled by the value of 2. All right. The next one we want to know is the frequency shifting property. Okay, if you see here, just now we see that the time is shifted. Okay, if the time is shifted, yeah, sorry. Okay, if the time is shifted, the function in S domain will be shifted by E minus ST naught. Okay, so the vice versa of the or the inverse of the frequency shifting, just now is time shifting, is also the same. Okay, so if you see the frequency is shifted by S naught, okay, in time domain it will be shifted by or multiply by E S naught T, and then they will be the original functions. Okay, so if you could see here, the frequency shift S by S naught. So in the time domain, it will be multiplied by E S naught T, the value of the shifted frequency, multiplied by its original Laplace. Okay. Okay, so this is what I mean. In the time domain also we have this one. If we shifted the time T naught, in the frequency domain it will be multiplied by E minus S T naught. Okay, T naught is the value of time shifted. Okay. Alright, so this is the same frequency shift. Okay, this is shift by plus A. So this will be the value of the E minus AT. Okay, so now let's have an example. Now we have T shifted by minus A, and also this is to confirm it is started at ut minus A. So this is actually a condition of this frequency. That means it will start at A. So in Laplace transform, or we convert it into frequency domain, cos omega t in frequency domain is in S divided by S squared omega squared. This is cos omega t. Okay, but now it has shifted by minus A, so we'll just have add this one, the exponential, by minus A. S is the frequency domain, so it's going to be E minus AS, value of the shifted, and it's XS. Okay, the Laplace transform. Alright, so for frequency shifting, okay, we know that there is an E minus AT here multiplied by a function. So this is the function xt. Okay. Okay. So in in frequency domain, we will have this S plus A. Okay. And shifted by S plus A squared omega squared. Okay. So for cos, actually the function in frequency domain is S squared plus omega squared. But since it has a value of E minus AT, which is a shifted value, so we just add here. Okay, and also here. Okay, same also with the sign. Okay, we add the S plus A squared at the frequency domain function, because we see that this is shifted. Okay, shifted by A. Okay. The next one is if we have a time differentiation property. Time differentiation property means that we want to d dt xt. Okay, in Laplace transform, you have to just add s in front of the Laplace transform of the function xt minus the initial condition. Okay, you can see also there is a second order. If the second order, that means you are going to extend this function. So mean the s also have second order as x as s squared xs minus the s multiplied by the initial condition, and also the d dt of initial condition at t equal to 0. Okay, so this is the first order. This is the second order, means that you have to include s squared. For first order, only s. And then the nth order, you will follow this formula. Sn fs minus Sn minus 1, the initial conditions, f0, and then Sn minus 2, the differentiation of f. Okay. Alright, so let's see this example. If we see this example, it looks like the differentiation property. Okay, time differentiation property. So we have to find the xs of sine 3t. Okay, so to find the t sine 3t, that means we will use the time differentiation formula. So t ft, so you just have to find the ft, identify it, and convert into minus df over ds. Okay, from the tables, okay, so we know that if sine 3t is going to be 3 s squared plus 9. Okay, but it not finished yet. That means we have to multiply by t. Okay, so using this formula, okay, so we have to add s xs. Okay, so you just d dt, the dds, okay, in time frequency domain, 3s squared plus 9 equivalent to this one. You are going to use the quotient rule, which is equivalent to v du minus u dv divided by v squared. Okay, right, so this is the first order, so you have to use the first formula. Alright, the next one is time integration property or frequency integration property. That means if we want to integrate a function xt and transform it to Laplace, we just transform it into xs but divided by s. Okay, unlike the differentiation, we have to multiply by s, and for the integration we have to divide it by s. Okay, and then and the inverse is if we have a function xt divided by t, that means we have to integrate it in the frequency domain xz. Okay, or xs ds. Okay, different depends on your variable. Alright, so if we see here minus t xt, okay, so we can convert this to Laplace transform and dds. Alright, so for the time integration and time differentiation, we also have the level of order. Okay, so it depends on the how many t in front of the function. Okay, for example, if t power of 3, so this one will be minus 1 power of 3 d3 fs ds according to the how many order. Okay, so just to refresh you on the differentiation rules, we have product rules, okay, that we are will be frequently used, and also quotient rule. Okay, that means if we have two signal, both have variables, we have to do the gx f prime x minus fx multiplied by g prime x and gx squared. Alright, so we continue. For example, this is the time differentiation. So t squared sine 2t ut. Okay. Okay, so for sine 2t, okay, when we see this, we know it's a time differentiation property. Okay, now our job is to convert this into Laplace transform, which is 2 divided by s squared 2 squared. Okay, so now to fully utilize the function, so we have here t squared, means we're going to have minus 1 squared and double derivation, or derive 2 times the 2 over s squared plus 4, which is the sine 2t. Okay, so since the degree is 2 here, so we have to minus 1 squared here and twice the derivative. Okay, when you do apply the quotient rule, you will have ds firstly once only, and then the second one minus 4s s squared plus 4 2 squared is from the first derivative, and derive it again here, and then this equation will follow the level of order in t. Okay, so you will get this answer. Alright, so the second last property is the time convolution and frequency convolution. Alright, so if we have the two signal convolve in frequency domain, we will just have to multiply the two frequency, no need to convolve. Okay, so the vice versa, if we have two function xt and ht is multiply in time domain, it will just have to be convolve and multiply by 2 pi g. Okay, so it's a pair. Okay, so this is the same, convolve in time domain, in frequency domain it will be multiply. Okay, so for example, we want to have convolve of EAT ut, means it started at t larger than 0, or it's causal, and the second one is the function EBT. Okay, so now we have EAT and EBT in time domain, so the function is, so the operation is convolve. So in time domain, so in frequency domain, we just have to multiply. So EAT is 1 over s minus a, and for the second one, 1 over s minus b is for the second one. So when you just multiply this one, and you will have this function. Alright, the last property is the initial and final value theorem. Okay, for the initial and final value theorem, usually we want to find the initial and final value of a function. Okay, but we know the Laplace transform. Okay, so the condition is the Laplace transform and of xt and dx over dt exists. Okay, the numerator power, numerator is here, and the denominator power m, numerator is n. Okay, so m must be less than n, so this one must be smaller than this one. Okay, Alright, so for the initial value theorem, we will substitute s approaches infinity, and then we multiply s with xs, the product conversion, and also sxs, s approaches to 0 if for final value theorem. Okay. Okay, so this is the conditions. Alright. Okay, so we will focus this one in the next class, and we will see the example of these two. So for example, we want to find the initial condition of this function e minus 2t cos 10t. Okay, so we just solve the cos 10t is s divided by s. Okay, for cos is s divided by s squared plus 10 squared. Okay, but now it will have a shifted value by 2, so you will add here s plus 2, and here also s plus 2 squared. Okay, so to know the initial condition of this function, we will substitute s equivalent to infinity, and this is the conversion of the function. Okay, substitute s into infinity, we will get the value of 1. Alright, so you just have to solve this function in frequency domain and then substitute the s to infinity. Whereas for the final condition, as usual, you have to solve the function, okay, and multiply by s, yeah, s fs is the Laplace transform, and then s is the condition, s multiplied by fs, and then substitute s to 0, so the final condition is 0. Okay. Alright, I will stop until there. We will continue this for the time periodicity. If you have questions, you can WhatsApp me or ask in the class. So we will continue the properties in the next class. Okay. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Alright, thank you very much.